New order, if you talk about almost close to 50%, and 323 about 48%. And if you see the year-wise delivery, to start from 2023 about 42 ships this year. Next year about 81, and subsequently in 2025 about 90 ships. That's a huge number. And 2026 about 49. So you can see this chart almost saying the same thing. 2026, 49. All the yards are booked. And if you see the price also, LNG vessels on sky high, close to $450 or $60 million, close to 2,000 crores rupees each one. And these are the containment. If you see LNG, percentage of total fleet right now mostly membrane vessels, in membrane vessels, and there are two companies which are pioneers in gas carrier construction. One is Gas Transport, and the other is Technigas. Both are French companies. They became merged together close to 2000, became GET, Gas Transport and Technigas. And if you see the percentage of total fleet right now, roughly about 36% of gas transport and 40% Technigas. And that is Technigas Mark 3. Mostly there are, due to the spherical cost, what we call about 15%. But if you see the future new order, there is nothing. So the future is gas transport, which is about 72% order, almost double than what is the existing number. And Technigas right now is about 40, but there are 21% order, the new order as you see. And this is the engine type, which MD Mr. Satya Singh will cover more details on this. But if you see maybe and next year, right now about 150 ships, with more than 150. But you see the order, it goes more than 400, and details you will be covering more on this. And next one is DFD and PFD, dry fuel, so you have about more than 200 ships. But if you see the order, not many. And same way, diesel booster, not many, the new order. The new order maximum 323, what you saw, mostly covering Behi and XDF. And so that's about proportion. The future will be mostly Behi and XDF in LNG vessels. And these are the containment. If you talk about what are the containment in new LNG, if you talk about self-supporting, is Maritime mostly.
The power again.
There is a new
power again. So starting में problem नहीं था ना? Starting में problem नहीं हुआ ना?
Yeah. So SPV stands for self-supporting.
I will tell you what to send. I'm sending you. Okay.
Yeah. So SPV stands for self-supporting systematic type B, and there are few new vessels which are 80. Delivery also 3 ships are there, and but not many in number as such. But the maximum in number, if you see on the right side, which is membrane, and there you have NO96, gas transport NO96, there is new design, and Mark 3. Also there is Mark 3 X and X Plus. And MOS, there are not many, but there are a few new design of X MOS. Standard MOS is about 140 km, and it is straight to close to 150 and gone up to 180. And so straight MOS is there, but in future as you see there hardly anywhere. So those design we call it as Saya Endro and Saya Endro, which is straight MOS 155 about, and the other one is 180. And we just cover each one, and this is the membrane type. Mark 3, there are a few new versions. Mark 3, last one, Mark 3, LO3, and comparatively much better on gas pump for 96 also the new design. And CS1 which came way back in 2003 or 4 but will not successful. Three ships have come out but after that nothing. So as far as the picture is concerned, it is Mark 3 and 96. Most of the yards in Korea and in China, so it is GTP, so either Mark 3 or 96 newer version. And so these are some of the numbers. If you talk about delivered and also in order, if you make it all together, 96 is about 354 ships. Present plus what have been ordered, about 44% of the total order. Mark 3 about 56. And these are the breakup. If you see on the left side, breakup about 26.7% in 96 plus, LO3 15%, and glass wool, DW glass wool is about 33%, but present is about 137, which is roughly about 39% of the number. And if you talk about Mark 3 next is about 61%. So that is covering most of it. The future is Mark 3 next design. I have some photographs also. And to understand gas carrier design, the most easiest way to understand is think about thermoclass. Thermoclass keeping your base or T. So here there is not base or T. Obviously, we are carrying cargo at about minus 101 degrees temperature, which is methane. That's the boiling point of methane which you carry. But obviously, the containment is such that it can take care of that particular temperature. So this is, if you see the thermoclasses, I said thermoclass, the glass design in Mark 3, you have 1.2 mm stainless steel membrane. Glass coating is replaced with 1.2 mm stainless steel coating, that is your primary barrier in Mark 3 design. And NO96, it is IVAR. IVAR 0.77 mm steel membrane. And I have some photographs, better photographs where you will be able to see. So this is on the left, as you see in Mark 3, that is 1.2 mm. But NO96, it is 0.7 mm bar. And then also there is primary barrier and also there is secondary barrier, is ensuring that the cargo is kept safely. And so this is how NO96 IVAR membrane, IVAR 0.7 mm. Now what is IVAR? IVAR is stainless steel alloy and 36% are nickel. Nickel is very good primary when you talk about low temperature cargo, that helps quite well. And what you see on the behind, we call it as tripod bars. So all your pumps and all everything you will be able to attach to that. All precision instruments are there attached to tripod bars. So this is how a tank look like. So the last coating on the thermoclass, this is the glass coating on it. And so this is primary barrier, which is IVAR 0.7 mm, and primary insulation, which is glass wool. Also, you have sometimes, and secondary insulation is also plywood boxes. So there are two light steel metallic membrane, two layers of insulation, primary as well as secondary. And so in NO96 it is made up of IVAR, where Mark 3 it is 1.2 mm. There are two options, both are successful there for almost last 20 years. From 90s, these two designs have come, they became successful. In the future, it will be both Mark 3 and NO96, and both are under GTP. GTP is when a ship is built, you need to ensure that the tanks are constructed with the design they are, and they ensure everything in case any problem also leak and all, they also look after. And these are some of the photographs of primary and secondary drain. So if you see this is the aero 96 and primary barrier is invar 0.7 mm. And primary insulation box is 30 mm. Secondary barrier again invar. So there are two invar membrane in aero 96, 0.7 mm very thin membrane. And secondary insulation box is 300 mm. Those are plywood boxes. And as you see the tripod mass on the behind, so that is liquid down and liquid down. So this is invar membrane NO96 under view, and nickel is 36%. That makes it better and healthy. And so this is NO96 design. So NO96. Now the latest versions are one is glass wool, other is L3, and the advantage is when you talk about boil off rate, every day how much liquid will evaporate and you have a lot. So with this new design, the boil off has come down from 0.15% of the whole volume to almost 0.07. So the third one, NO96 Super Plus, close to 0.07 of boil off, and initially it used to be 0.15%, which is accepted in that part. Now it has come down. So these three designs, which ensure that the boil off control compared to less, and also many of the designs are now with PRS and FRS, so that also helps in a way. So this is the insurance in 96. Same way we'll see also Mark 3. So you see the boil off on the left, if you see initially it was 0.15%, come down to 0.2 glass wool, NO96 glass wool, TW gas glass wool, 0.15%. And with LO3 it is about 0.10% boil off rate, where the liquid will evaporate and produce so much of vapor that you have to control, either with the Cmmi or USDF or daily. And NO96 Super Plus will come down to 0.65. From 0.15, it has come down to now 0.3. So better energy efficiency. And live boxes, as you see on the screen, this is how it looks like in glass wool and LO3. They are always actually foam. Super Plus also with foam. And this is another view of environment range 0.7 mm. This is NO96. And this is the primary box and secondary boxes in NO96, your design. This is glass wool and NO3 plus design. With your secondary boxes and now with primary box. This is Berlin glass wool green, NO96 glass wool design. And in USA. Which is the NO3 design. Primary and secondary box. This is foam. And if you try input with the new NO96 design, now we use the for Mark 3. Primary boxes and second box. This is 1.2 mm stainless steel membrane which is for Mark 3. And So what you see is 1.2 mm stainless steel, but it will be reinforced. And there are compressions, two compressions each, and what you like corrugation, sort of, not corrugation, but so this is the IPS. So what we call the primary barrier is 1.2 mm stainless steel, secondary barrier is 0.6 mm reflex, and what you see the yellow color is the IPS, interbarrier space, and they are generally pressed with nitrogen. You have to do nitrogen generator. So that takes care of. So in case there is any leak, you come to know with nitrogen pressure. So there are some settings also for IPS and IS. The pink color, what you see, IS, insulation space. And then the copper dam and the inner wall. This is another view of Mark 3, and this 1.2 mm stainless steel plate. And this arrangement we call it as waffle plate arrangement, and that is good for cryogenic. So when you talk about low temperature cargo, it helps. This is the it is magnified with primary barrier is 1.2 mm stainless steel plate. Primary insulation is 100 mm, and the secondary barrier is reflect. What is reflect? We will see in the slide later, and the secondary insulation is 170. So this is the other view of saying. So what you see the primary barrier is 1.2 mm. What is protruding out is those are the waffle plate arrangement. So that takes care of your expansion and contraction better. Especially when you're cooling or you're warming up, going to dry off, so and also for cooling down while going for loading, so this helps. Secondary barrier is replaced, and we are polyurethane foam in installation. This is a triplex 0.6 mm, which is combination of glass cloth and aluminum foil. Thickness is 0.6 mm. Again, it is very good cryogenic, and this is used as secondary membrane. The cost Maritime standard design cost is about 1,47,000. Basically, where you see it protruding out on the blade, and so that is being increased to a size which is stretched to about 155,000 because the design is high and low. And another design stretched further on the bottom as well as on the top, so that we can 122% close to 180K, and that is the higher rainbow design. If you see this, this is how what they did is both the sphere is about the diameter 41.5 meters. The height is increased by about 1.5 meters. 41.5 with 43 meters. By increasing to 43 meters, they put one cylinder, long cylinder 1.5 meters, and increase capacity by 8,000 liters. It becomes 155. With that Japanese design, which their chips have come out with this design, and same size also 180K. And so these are the new MOS design, which is being, and there are some with continuous tank cover, where it is covered, number 1 and 2 are covered, and then same way 3 and 4 in between are 9, 4 and 5. And so those are the new design, which is called stretch MOS, not many, but there are few. And it's now the it helps in weight resistance, fuel saving, and maintenance. So these are with continuous tank cover. And so this is the last design, which is SPV, because there is somebody pneumatic type B. It can take the weight of the cargo on its own, and so it is well supporting. And these are not many ships of this particular design, and about 5 or 6 ships. And so they are like a LPG tank, centerline bulkhead, so it is completely different than any other LNG design. This is not very like coastal tanker design with centerline bulkhead and swath bulkheads. So this is slightly different, and there are supports. Bottom there are time supports and boards, which is mostly there in LPG ships, E-grade LPG ships, which is of similar design. Supports are there, and you find centerline bulkhead also. Those are, we call it independent type A. This is type B, and so this is few ships are there. 2018 also few ships have come out, and this is void space for inspection. It go inside and inspect the tank and the boards. This is all the tank support, and sometimes you see the seaway also tank moving. And this is the tank supporting type B design. And so this is how the ship will have ship type B. This is XPB. Then supporting prismatic type B is our against the manifold, and which is slightly different than NOS as well as thank you.
Thank you, Tapan. That was an excellent, very interesting presentation. Okay, thank you very much. I will now invite Mr. Satish Kumar Singh, MD of Molmi, to talk on LNG propulsion system. Good evening, sir.
Yeah, good evening.
And you're well, yeah, loud and clear, sir. Please go ahead, sir.
Yes. Thank you, Dr. Satish Kumar. On behalf of Cmmi, everybody is gathered today. This was actually not a presentation from my side, it is Captain Panda. But regarding the LNG propulsion, some small overview that I will be giving this occasion. So thank you everyone for gathering. This subject of LNG propulsion. LNG basically has been in the last 20 years as the most dynamic into LNG propulsion options basically exploring. No other type of vessel have ever needed actually to explore the LNG different propulsion options. They were all standard either 2-stroke or 4-stroke diesel engine. So why basically propulsion options are needed to be explored different in LNG is one of the challenges which the membrane system, Captain Tapan Panda was mentioning, that MOS and membrane and different SPB, all these changes are happening over a period. Actually, in 1964, when LNG started, the boil rate used to be 0.25% per day, meaning if 100,000 meter cube cargo is being carried and 0.25%, that is 250 meter cube of cargo will boil off due to heat ingress if your insulation is not effective enough or whatever best we could put. But over a period, everybody was trying and it has been improving, and now it has come to 0.08%, which is just 80 meter cube of basically boil off due to heat ingress, because there is no perfect insulation in the world. So the best insulation maybe nowadays
the perlite which is being used is coming from the volcano, volcanic eruption. That is one of the best physical insulation. And for that, the heat ingress is minimal. So LNG has evolved over a period, and the best of the best latest design is 0.08% of boiler related, you can say losses, so you can utilize it. If you do not utilize it in the engine, you have no choice but to throw it or burn it. Those are the options. So either you throw it, but if you throw it, the methane, which is the predominant in LNG, it has got 30 times more impact on the global physical warming, etc., compared to CO2. So that is surely not a good idea. If you burn it, still you create a lot of NOx and CO2, etc., etc. So the best is that you at least utilize the energy, which is much more than the value of it. The calorific value can be much more than diesel or HFO. So why not utilize it? Anyway, it will be boiling off. So the whole LNG industry had no better choice than to consider different propulsion options where maybe they can utilize the LNG as a fuel and better save the cost of the bunker. And so that is the reason that we talk LNG propulsions differently than other type of vessels. So now this has started, this whole industry started with the superheated steam turbine. And for a long period of time, maybe almost 35, 40 years, there was no competition to superheated steam turbine as a propulsion option. This was very, I will say, reliable, not so efficient, but it continued because of the reliability for a long period. And only after 2005, the diesel industry basically they started to challenge propulsion option. And then came different options, as you can see, some DFD, TFD, DRL, high pressure. I will come to all of this briefly. So, broadly, if you will see the volume of gas, which is anyway going to be generated inside the tank when you are loaded cargo, you have to somewhere you have to consume. You are consuming. Your options are steam turbine or dual fuel engine or gas turbine or direct diesel engine and reliquefaction plant. These are the options basically you will be using. So this, if you are using a steam turbine, which was mostly being used, by 2005, maybe 99% of the propulsion was only a steam turbine. Only from 2006, things have started changing. And today, the steam propulsion is only 31%. So in the existing vessels. So you see this last 18 years has been real emergence of different propulsion options. So this steam turbine, conventional steam turbine, there are some advanced steam turbine, which is the ultra steam turbine. Then there is some dual fuel engine. You hear basically it is also called as a tri-fuel diesel electric or dual fuel diesel electric. Here you can use basically the diesel or you can use the gas and you can use the electric drive, basically two big propulsion motors instead of the diesel main engine. There is no main engine, only generator, and then creating a lot of power. So 40,000 kilowatt of the power generation, and you can bring to the motor and maybe 26,000 kilowatt of the motor only for the propulsion motor, and you can continue to drive the same. So that is the dual fuel type of option. Then you have some gas turbine, though this option is approved by classification, but there are not many takers, except maybe some naval basically forces, etc., for small purposes they are using. And then there are some diesel engine, which is basically with the reliquefaction plant. Reliquefaction plant in LPG is very, very common matter, but it is very, very uncommon in LNG industry because it consumes a lot of huge power. With up to 5 kilowatt power, it can consume on a big related plant vessel with operating full capacity. Not specific for VLCC, LPG, bulk container, seagoing power itself can be 700, 800, 1000, 1200, 1500 kilowatt. But 5400 kilowatt only drilling plant taking the power guzzling capacity is so high that many of them do not want to choose for this option. And that is why drilling plant option in LNG has remained basically not so much chosen option. Now, if you look efficiency, why do we choose at the end of the day, efficiency of the propulsion? So, a steam turbine, typical steam turbine has been very, very useless in the efficiency terms. Only 30% of the thermal efficiency. So, when fuel was cheap, nobody bothered for the cost. Maybe it was going on 1960s and 70s and 80s, and it was reliable, it was fine. Nobody questioned this efficiency matter, and it was the only solution. Then, very, very recently, when the diesel industry has started to give many solutions, the steam industry thought, why should we remain behind? So they tried to challenge, and they tried to give UST, you can see, ultra steam turbine. They came with a higher efficiency, higher newer technology, steam propulsion, which is 35% efficiency. DFD or TFD, this type of option is a 4-stroke engine, where you are basically burning the gas or diesel, creating a lot of electrical power and running the propulsion by the propulsion motor. Then you have SSDR, which is basically slower speed diesel ship with the ready axle plant. This is only typical normal diesel engine, say Cmmi engine, and it has no gas injection. It is only all the LNG only getting BOG, boil of gas is getting only re-liquefied. But engine is absolutely normal, like any other VLCC, Bulgaria, container, etc. Then you have speed dual fuel engine. We will talk about that later. We also have something called OGAS system. Again, it is to do with the gas turbine, basically, option, which is still not many takers are there, so we will not be going into this. These are also not so efficient. Now, nowadays we keep talking about tier 2 or tier 3 and those requirements, and this is also one of the things which is pushing the limits of various engines. So quickly, if you see that how does it fare, the steam turbine is basically meeting tier 2 from the SOx point of view. NOx point of view, basically, NOx is less because the heat creation is basically less, but if you are using 50% HFO or 50% gas, under that condition, it has been basically compared. If you see the slower speed diesel engine with the re-liquefaction plant, then it is not meeting the TFD requirement. TFD is able to meet the TFD requirement. The low speed diesel fuel, this is not meeting the TFD requirement. So regarding this, little bit, once I will go further, it will be a little more clearer. But bottom line is, if you see on the top, XDF, it is meeting IMO tier 3. What is tier 3, tier 2? If you go to ECA area, etc., you need to meet the tier 3 standardization of the how much is the NOx emission is happening. So only 1.8 to 3.4 gram per kilowatt hour, that is the range depending on the speed of the engine, is the IMO tier 3 requirement. So this requirement is being met by XDF, but not being met by Navy engine, MEGI engine. This requirement is met by DFD on the gas mode. It is being met by the gas turbine mode, that is a COGAS system, or by the stage propulsion option. So, if you see the environmental profile very quickly, XDF, when we say XDF, what is this? This is a 2-stroke engine. It is a 2-stroke engine where the gas is being injected at about 8 bar per second. If you say the MEGI engine, it is a 2-stroke engine where at 300 bar per second the gas is being injected. So the difference of XDF and MEGI is both are two-stroke engine, but XDF is at low pressure gas injection and MEGI is high pressure gas injection. And then there is a diesel or HFO, normal standard engine. So you can see the particulate matter, SOx and NOx related general profile differences. This is the thermal efficiency, reliability, OPEX. We will not go into the time limitations in this detail. To have a basic overview of this typical schematic diagram of a steam step. You will see the steam step. Simply to understand from the cargo tank, the volume of gas is elevated, it is getting generated. Every day due to the heat increase, due to no perfect insulation ever. That volume of gas we are taking out instead of throwing or burning, we are taking out through some compressor, which is a centrifugal compressor, we call it a volume of gas compressor. Now it is a high speed, maybe compressor, which is basically pushing at a low pressure the gas, LNG volume of gas, basically we pass it through heater, etc. at the high temperature. Finally goes in the steam turbine vessel to the main boiler. Main boiler is a big boiler. Now, on the normal ship, you come across auxiliary boiler. Just give you auxiliary purposes. But this is the main boiler, which is giving you a steam to run your main turbine and run your main propeller shaft. So using this main boiler, we are creating the steam, taking it to the steam turbine, and finally to the state that is high pressure turbine and low pressure turbine. We are combining the gear system and we are basically moving the propeller shaft. Simply to say, steam propulsion option is this. We have to take the gas, take it to engine room, okay, make it work in the boiler, burn it, create a lot of steam, run the steam turbine, let the steam turbine drive the propulsion system, and run this. So the efficiency is best because of the steam turbine design matters. Now, so a steam basically world try to push and make it more advanced instead of the 60 bar boilers basically on a typical steam turbine vessels. It came with the 100 bar pressure, where the high pressure, intermediate pressure, and low pressure. The stage of turbine was created through a reheat cycle. And this gave a little more 5 to the 4 stroke engine or DFD. It became comparable, and some of the vessels in the world came with this option. It is also called ultra steam turbine. So superheated steam turbine, the standard ultra steam turbine, the efficiency basically changes, the steam pressure, steam temperature changes. And there are some further ultra steam supercritical turbine, etc., which is now here. What power you are getting here? It is coming through USCT, ultra supercritical turbine, where the water changes to the steam or vapor phase without going through the intermediate process. It is above the critical point. So those type of boilers are different type 300 bar pressure boiler. So these things are being used on the side. On the set, they are considering to push this type of design to give a 5 to diesel engine basically options. So we just discussed regarding the steam option, which is now reducing. And this is a TFD or DFD, basically two terms basically being used. It has been just a DFD basically has been upgraded to a term TFD long back. But people do use DFD as a more common word. It has got a technical difference. I will not go with that as of now. But here, very simple. You have only the 4-stroke engine generator where you burn a lot of gas, LNG vapor. You can also burn diesel and create a lot of electrical power. Bring it, run two huge motors. In place of the main engine and the engine room, find two huge motors. That connected to the gear system which will drive your propeller. So it is an electrical propulsion. So burn gas or diesel and create electrical power, bring to electrical propulsion motor and drive your propeller. This is the TFD or DFD terminology, which is basically, you can see this works on some principle which is called being burned principle. As you can see, that there is a gas admission valve where it is written in the green color on the top in the cylinder head. There is a gas entering at about 4.5 bar pressure. And there is a pilot, basically injection system is there where 1% equivalent of the pure diesel basically is being injected. Gas is entering from the side, inlet valve. This is a four-stroke engine, TFD engine. The gas is entering. When the piston is going down, gas and air is mixing basically. And when it is coming up, it is trying to compress. When it is coming near the PDC, a pilot injection of the diesel just injects, supports the fire, and the firing takes place. Rest is done by the gas. 1% support is by the pilot injection, that is basically this. So that is the basics, which is basically lead burn principle. Here, there is something called air fuel ratio, which is adjusted to higher side, that is around 2.5 instead of a typical 1.4 to 1.8 air fuel ratio. That is required because a typical one engine to have basically a capacity to burn the diesel or to burn the gas is a technically a lot of issues of compression ratio, etc. So for the gas burning, you have to go into the more lean burn principle or more air fuel ratio has to be changed, then only nozzle effect, etc. will not happen. So that is the TFD related stage. This is another type of business where you will see there are two propeller shafts. One propeller shaft is being run by the steam turbine. The another is like TFD engine electrical propulsion action. So both are combined, A plus B. But we just took the steam. Instead of the steam, under steam turbine is the one part which is running the one of the propeller shaft, and the TFD is running the second propeller shaft, and together it is moving the LNG vessel. So this option is basically the steam and also gas, both the combination basically the electrical propulsion, both combination. This is termed as a stage propulsion. Now, this is a gas turbine electric. I will not get into it because it is not getting an order book. The gas turbine it is same like your aeroplane. Boeing 777 is 30 gas turbine. The same turbine is basically being converted here where you burn the LNG vapor, create the whatever is the energy exhaust is created due to that. You use that to run a turbine and you connect the alternator and create a lot of electrical power and finally run your electrical propulsion. So that is the option which is a gas turbine. Then it comes slow speed diesel propulsion, which is a very conventional diesel engine. Like there are two main engine, Cmmi engine here. So it is a electronically controlled but conventional engine. So, any capability of gas burning. So there is no gas burning in this engine. But on this vessel, we have a really plant vessel, really plant where your LNG vapor which is coming out of the boil of gas, not going to the engine, but getting re-liquefied and going back to the tank. So boiler is not wasted or burned or thrown, but engine it is not being used. It is a conventional engine. Then you have this is a two-stroke engine, but instead of the previous slide what you saw, in this case, you have gas can be burned inside a two-stroke engine. The gas is being injected instead of a fuel injection at 300 bar pressure. The gas can be injected at 300 bar pressure. It is a compressor ignition cycle, a standard two-stroke cycle, but it has got the DO and gas, both injectors are there on the cylinder head. So this is the MEGI engine. Many of the IGF vessels today nowadays what is coming, your container, valve, PCC, everywhere the LNG fuel engine when it is coming. One of the options they use is the MEGI engine also. So MEGI engine is nothing to do that it will be used only on LNG carrying vessel, but this is also for the IGF vessel where LNG is used as a fuel, whether the bulk container PCC wherever. There are of course LNG tank for the bunkering you have to keep. and from there the LNG can be taken in the similar engine with certain parts, just a small modification. Basically, that is what is being used, and this will become the future. Many companies have adapted for the future IGF vessel with MEGI option. This is another option which is the most latest, which is getting very popular. It is a 2-stroke engine, but not at the 300 bar pressure gas injection, which becomes little technically complicated, very costly. Capex increases to reduce the capex. To reduce the capex, reduce the cost, to inject the gas at only 8 bar pressure instead of 300 bar pressure. This is the option which is involved. This is also one of the type of vessel which is an IGF vessel also getting installed. So XDF is the latest from BGT or Wärtsilä front. Instead of RT Flex, the bigger or newer brother of that is the XDF. Basically, we can think that way, but the gas injection at a low pressure. This is what you can see here. There is a pilot injector with a feed combustion chamber. We have a gas admission, and the gas can be admitted in the, you can see in the middle of the liner at the 8 bar pressure. It is based on auto combustion or the lean burn principle. So this is the most in the traction now. I will skip this. The XDF vessel has the ultra low NOx emission, meeting the Tier 3 requirements. It has got, but it has got one challenge, one that is called methane slip. When the low pressure gas injection happens, some of the gas leaks out through the exhaust without getting burned. And that increases, that will increase the global warming potential, etc. So there are another challenge to that, another method to that. There has been further evolvement of XDF second version. In this regard of the GHG emission, MEGI engine, which is a high pressure gas injection, is more effective than the XDF. But XDF has the total capex, OPEX, all these front. The XDF is superior than the MEGI. MEGI is only Tier 2 standard meeting, not Tier 3. So there is a conflict of the maybe is better or XDF is better due to Tier 3 and Tier 2 requirement. Still, the XDF is getting the frontal traction. Now, to give a fight to the Wärtsilä, the man BMW, basically the Navy was not getting big traction. So they came with the challenge of the MEGA or mega engine. This is also low pressure gas injection, something like XDF contemporary. And 5, it is a new engine. It's going to be delivered next month for the first engine, basically. So, but in the order book, this is 130 vessels with the mega engine has been ordered, and about 130 with the XDF engine has been ordered. So both are competitors now. If you will see from the price, the freight rate, etc., typical comparison, you will see 16,000 to 39,000 to 54,000. These are the charter rate, depending on the type of. This is the steam. For the steam type of a vessel propulsion options, the pricing. What is the pricing? Of course, there are high, medium, low, different options. It depends on the what is ongoing gas rate. Basically, based on that, this charter rate has been fixed. But you can get an idea that a 2-stroke engine is getting more and more traction and higher pricing, higher market demand compared to TFD, which is a 4-stroke or ST. So, TFD is better than ST in general from charter rate point of view, and 2-stroke is being preferred. And after 2-stroke, there is a high pressure and basically low pressure, basically options. So you can see here that today on the left side you can see 31% in the global fleet is a steam turbine, 26% is MEGI or XDF, DFD is 33%. But what is order book? 87% is MEGI, XDF, MEGA, etc. And 13% is DFD and steam turbine, nothing on order. So What is the trending? Trending now is WinGD XDF, which is a two-stroke engine at low pressure, and MAN BMW MEGA, which is also a two-stroke engine with a low pressure. This is the engine or propulsion option maximum on order as of today. So that's what we discussed. 87%. If you split this, almost almost is XDF and MEGA. So this is the in nutshell. I've taken already 7 minutes more time. Sorry. So in a nutshell, what is the different propulsion option which is available in the LNG market? Okay. So we have no time to get into further detailing. In case of you have any questions or something, I will be happy. Thank you.
Thank you, sir, for a very comprehensive and excellent presentation. We will take 5 to 10 minutes. If I don't see very much on the chat at this moment, if there is any questions, please put on the chat. Those who are physically present can also, if you have any questions, please. Well, I think we don't have any questions at the moment. So feel free to send us an email and we'll get back to you from the speakers. I would like to invite Captain J.S. Kanwar to kindly hand over the Cmmi memorabilia first to Mr. Satish Kumar. Kanwar, sir.
Thank you so much.
Thank you, sir. Please, thank you very much, sir. And I must once again thank Mr. Satish Kumar for the very comprehensive presentation. Thank you, sir.
Thank you.
And now I'll request Mr. Kanwar, sir, to hand over the memorabilia to Captain Tapan Kumar Panda. Thank you, sir. Thank you very much. And thank you, sir.
Thank you very much for.
Thank you, sir. Yeah.
It's an honor to give the.
No, sir. It is our honor that you are here, sir. So before any ado, I will get into the vote of thanks. I'd like to thank the office bearers, wardens, senior members of the shipping fraternity, and all the participants who have come here today. I would like to thank the management of Molmi, especially Captain Albe, who has given us this opportunity and the venue for our monthly lecture on new LNG vessel design and containment. I would like to thank Mr. Satish Kumar, MD Molmi, was kind enough to give us an insight into LNG propulsion. Sir, very comprehensive, excellent presentation. Thank you, sir. I would like to thank Captain Tapan Kumar Panda, who was kind enough to give us insights into a very detailed, excellent presentation on LNG vessel design and containment. Anyway, it was new to me from what I was going through. Thank you, sir. A big thanks to the office bearers and the master of Cmmi. I would like to thank the media, Marex, Seajob, Bandarkar Shipping, Sailor Today, Saga Sandesh, and Maritime Destination. Once again, I thank a special thank you to Nangia for Sailor Today YouTube. office team, Mr. Sudhir Palkar, for the backend support. Last but not the least, I thank each and every participant for attending today's lecture meeting. I would request Captain Albay to request those who have come there to join you for tea today evening.
There is snacks kept in our pan. You can please help yourself with the snacks before you leave. Yeah, and also the feedback sheets are put up. Can please put in your comments and give it back to us. It'll help us.
Thank you, Albay, for your help and assistance. We will now we will sign off from the Zoom. Thank you so much. An excellent preparation, and I think your hybrid mode is one of the best I've seen till date. Thank you,
Thank
sir,
you, sir.
and good night.
Thank you, sir. Good night.
सपनों में तू, दुनिया मेरी है वही तू है जहां।